Okay. So, good. Oh gosh. If I, oh, oh gosh. What a terrible. Sorry. Audio was off. Okay. Fortunately, I have audio back up. So we're just going to splice it. Okay. Sensitivity analysis. One of the key steps to understanding basics of model behavior, robustness of model results, for prioritizing calibration, and for prioritizing exploration aimed at intervention, is performing sensitivity analysis in the model. When I speak about sensitivity analysis, I'm talking about varying model assumptions writ large and examining how the model responds when you vary those assumptions. There's many types of parameter variation experiment. I'm not going to parameter variation types of sensitivity analysis, and I'm not going to be able to do justice to them. We can taxonomize them in many different ways. They include, for example, whether this is you're doing it with respect to parameters, so assumptions in the sense that they're encoded with parameters, or are you doing structural sensitivity analysis with respect to the impact of model structure on the results? For example, if you were to have two states in a state chart representing active TB, so one non-infectious TB, active TB, and one infectious active TB, how much of a difference would that make? Changing assumptions about the model being used. This is a different form of sensitive analysis, but there's a wide variety of types you can do just with respect to parameter values. A common way you'll see using the medical decision-making literature, you can talk about one-way sensitive analysis, multi-way sensitivity analysis, and there's questions whether you're examining things in a grid, for example, some sort of regular structure, whether you're drawing the values of these parameters from distributions, whether you're examining the results of these sensitivity analyses on a static basis or a dynamic basis. In other words, is this parameter being drawn from a distribution over time, or is it a single value that's assumed to apply all through the model? Some of the discussions here have some conceptual tie-ins with some more advanced techniques known as predictor-corrector models, models for sort of over time trying to identify parameter values of greatest relevance in a way, correcting parameter values in a way that will deal with an incomplete model. Certainly, when we conduct these processes, some of our interests have to do with sort of understanding the impact of different policies. So, for example, systematically examining the impact of policies of undertaking smoking-related interventions on 3 different smoking-related behaviors for different age groups and different sex groups, for example, and examining the output. This model is already open, which is good. I'd like you to click on the Monte Carlo 2D histogram experiment, and I'd like to conduct a basic sensitivity analysis of the sort that AnyLogic supports through its default parameter variation experiment, bearing in mind that you can perform much more sophisticated types of experiments, including hypercube or variations of that, either in a custom experiment, which is available in the professional edition, or by deriving those values externally, as Scott said, and imposing them on the model as specific values to assume, either of which is very doable, the latter of which is particularly straightforward given the skill set, the level of the skill sets many people in the world. So if we click on this experiment, what you'll see is for each parameter here, we can specify not just a fixed value, but a range. When we last ran it, for that examining effects of stochastics, we were examining it in a fixed level. In other words, we weren't varying the parameters. the parameter values. In other words, we weren't changing the model assumptions. We were just seeing how model output differed for the same assumptions exactly, just with different vagaries of the stochastics involved. Here, we're going to be changing the model parameters so they're drawn from the range. Yes?
Actually, when they look at the model look by default, it's actually put on freeform, not on variable range. So you need to see what you're seeing there. You have to put on variable range.
Right. Okay. Thank you. Yes. So you will need to click varied in range. This should be highlighted. Thank you, Scott. Let me go highlight this for future generations of students. So pardon me while I just fix this up. Okay. So okay, and then this will be click on varied in range. Click on varied in range. So sorry about that, folks. Okay. So once you do, sorry, not that one. Oh man. Sorry, this guy there. Okay. Okay. So let's go back to this guy, and we're going to click on varied range, and then we can click on range, for example. And I'd like to set this first one to be 5 to 25 with a step of 5. And what that indicates is that there'll be 5 possible values, 5, 10, 15, 20, and 25, okay, that we'll assume. So here we go. And a step of 25 of 5, okay. Right. You'll notice, incidentally, that when you chose varied range, the number of runs is grayed out. That's an indication of the fact that if it's exploring a grid, what defines the number of runs is the size of that grid. It's not something you impose on it. It's if you define only 5 values with respect to a single parameter, it will be 5 runs. So let's run this one-way sensitivity analysis. We're only varying this thing. Okay, who needs a TA? Who would like a TA to help them? Okay, TAs have been dispatched. Okay, who else would like a TA? TA? Yeah. So you have to click on varied in range, and then you have to change this to range from fixed, okay? Yeah. Okay. Sorry? No. So we'll do done here, and what we'll see is output from this with successive values of the run. Here it's only running a single time for each of these alternative values for this parameter. So can anyone posit what these sort of rough trajectories that you see are? I'll give you a hint. How many of them are there? 5. What do you think they represent? So here we're changing, we're adjusting the average illness duration to go from 5 to 20 to 25. So what do you think those represent? Good. And which is 5? This one or this one? We're having a longer average illness duration lead to more people probably being infected, or fewer people being infected? That's the long one. And in fact, when it drew them, I don't know if you saw it, but kind of put them in. So this is the 25. Okay? So this gives some sense of the sweep. Now, what I haven't done here, and what Scott may have been referring to, is that each of these has some variation around it associated with stochastics.
Yeah, that's what I get out of it, because I got a really look at 5
Yeah.
and I have a fixed it.
Okay, so what you may be seeing, I'm not sure about your particular settings. Perhaps the TA could be dispatched to help elucidate what's going on. But it may be that you're looking at, because for each replication, you may have replications enabled. You may have clicked this before. And if you were to click on, and maybe I'll ask the class to do this, if you click on replications here, if you were to enable them and we were to say 10 replications, then what we would see is each of those values of the parameter we run 10 times. Why would we do that? Why would we run each one, say, 10 times? Or why would, I'm sorry, yeah, to see if they're really different from each other. So in other words, we want to gain confidence that what we're seeing here in those differences is something more merely than the vagaries of stochastics, that there really are sort of gaps between them that are statistically significant once we consider the variability for a given parameter value, set of parameter values. There's going to be some variability around that, and to what degree are these really separated? And unfortunately, it doesn't display too clearly on the board, but you know, for mine, I could still make out five different trajectories, although one would have to really examine them with a non-parametric statistical test to see the degree to which they really substantively differ at a given point. Okay. Anyway, what we've just seen is we can use replications together with parameter variation, or we can do it without it, just run it a single time for a one-way. Ladies and gentlemen, let's examine a multi-way sensitivity analysis. So I'd like to vary here the infection probability in the range from, this is actually infection hazard, it looks to me. Okay, what, I don't like you calling it infection probability. Let me go see what's going on here. I have a feeling this is just using infection hazard here. Yeah, it's just okay. Oh man. So it's okay. So basically, what's going on is this is a model of infection spread, and we have infection spread occurring. Well, you could tell me. What does this mean? So this is a great little pop quiz. Okay, so this is the model. How did I get to this model? How do you think I got to this model? Okay, it's a person. Well, it's some person, you know. And this is the model that's running behind the scenes. You notice there's no visualization of the standard model. In other words, the standard model visualization is suppressed. This is a nice side effect of parameter variation experiment you may want to exploit. If you want to run your model faster by disabling visualization, run this parameter variation experiment one time. It may run a lot faster because it doesn't have to display things on the screen. Any logic? Let me repeat that. I've heard of models where people ripped out all of the visualization components because they wanted their model to run faster. You do not have to do that. If you want it to run without visualization, without the overhead of visualization, run as a parameter variation experiment a single time. Okay? That will allow it to run in a headless mode, as we say in computer science, without the need for sort of a visualization. Technically, it's not quite headless, but I'll leave that for later. Okay, so here what's going on is when we have contact occurring, there's a rate at which messages are sent by the contact rate times what it calls the infection probability. Now, this is actually a approximation that is used, and it's actually a very good approximation that can be used to reduce the number of messages a lot. The idea is, suppose you only have a 1% chance per contact of actually infecting the person. Only a 1% chance per contact. You really want to send, and suppose you have a contact rate of 100 people per day. Rather than sending 100 messages per day, and only 1% of them that land uninfected bearing fruit, you send 100 times 0.01, In other words, one message a day to somebody. And it saves basically a whole lot of replications of messages that they don't end up having an effect anyway. This is something that can really make a difference in terms of reducing the computational burden associated with your model. And it's something that it's most naturally placed in the lecture I give on performance issues. I think it may be one of the examples I include there in my performance-related lecture. But what's going on here? So who is this message being sent to? So say one message a day or whatever. The multiplication. Who's it being sent to? Person, the entire population. So this is not random connected. It's not random neighbor. Random neighbor will be in what? Neighbors in space. Random connect would be neighbors in a network. Here it's just a random. It's just anyone in the population. So it's random mixing actually. But the notable point is they have this rate is dictated by the contact rate times this infection probability. Now what gives me the willies is that that in the parameter variation experiment down here, we have infection probability of 0.8, and in my slide, I had go from 0 to 10. Oh man, don't follow that heedless sort of logic. Make this go in range from 0 to 0.1. Okay, to 1 to 1. With a step size of 0.1, okay? I'm going to deprecate this. What a bad, really, really inappropriate. Okay. Okay, so I'm just going to, sorry folks, I just want to take a shot of this so I can get rid of this monstrosity. Okay. Okay, so we're going to run it from 0 to to 1 with a step size 0.1. Who needs a TA? Who needs a TA? Okay. Okay, so there we go. And this should be 0, 0.1, 0.2. Okay. Okay. So, sorry. Okay. Good. I don't want to make use of that. Okay, so you should some output, which is multi-way output. And what this means is that it's doing how many runs here? How many different values are there here from 5 to 25? 5, 10, 15, 20, 25? 5 runs? How many for this later one? 0 to 1 by 0.1. 20, including both 0 and 1. 11. So we have 11 times 5, 55 different runs, right? Does that make sense? It's a grid, 11 across, 5 down. Does that make sense? Okay, so it's doing this exhausting. As Art noted, as Scott noted, there are much more artful ways to do this, which may become important if you when you have a larger number of things. Now, ladies and gentlemen, I can actually see it on my screen quite well, what's going on here, but this projector is not bringing it up. Can you see it on your screen? Yeah. Okay. So you see some trajectories over a wide range. There's some that are cresting up down here, some that are cresting up here, a lot that sort of go here, but it's much more diffuse, much more diffuse. So this is a multi-way sensitivity analysis within any logic.
And that is with replications or iteration.
Correct. That's right. If you put 10, each of those will be run. So each specific scenario with sort of some specific set of parameter values will be run 10 times. Yeah.
You mentioned before that you have reduced the number of messages by doing that.
Yeah.
That's right. How do you get to the idea that that's possible? I mean, I'm not sure I got the idea of that you said, well, it's only 72 people that are
Yeah.
not here.
Yeah, okay, so here's the argument, here's the reasoning. It's a great question, and I admire your rigor in asking this. Okay, so the question had to do, ladies and gentlemen, pardon me for just a second, I wanna,